We now look at the rare earth elements for magnets and motors. We can make the following observations. 95% of electric vehicles use rare earth drive motors. The quantities required worldwide will grow from 5,000 tons in 2019 to approximately 40 to 70,000 tons per year by 2030. More than 100,000 tons of rare earth permanent magnets are consumed each year in renewable energy, machine tools, robotics, and the other mentioned applications. And it is less than 1% of recovery of rare earth permanent magnet scrap in Europe. So this represents a large potential resource at a low carbon footprint. Here we explore the rare earth elements and magnets in more detail. The left graph shows the natural occurring rare earth element balance in a typical ore like bastnäsite or monazite. That is also called the rare earth basket. And we can see that the abundances of the different lanthanide elements differ greatly. Each kilogram of neodymium oxide produces 2.3 kg of cerium, 1.6 kg of lanthanum, and 0.02 kg of terbium oxides. Neodymium iron boron 214 is the most powerful magnet. It contains about 30 weight% of rare earth metal. In electromobility, we need about 700 grams of neodymium per electric motor. For wind energy, we need about 200 kilograms of neodymium per megawatt in a direct drive wind turbine. So can we find an adequate substitute? So this right graph shows the main figure of merit for a permanent magnet, which is the energy product BH max for various materials over a wide temperature range. Again, neodymium iron boron 214 is the most powerful magnet at room temperature. At high temperature, we have the aforementioned samarium cobalt type magnets, which are the best material. So, can we develop a substitute material? Can we, for example, make use of the so-called free rare earth cerium? And can we fill the large performance gap here indicated in green between the low-cost and low-performance ceramic ferrite magnets and the high-cost, high-performance rare earth-based magnets? So substitution is complex and has many levels of consideration. There are no easy answers, and the boundary conditions of the system and the application, as well as its usage, need to be properly defined. The viability of a substitutional strategy needs to be proven by life cycle analysis and life cycle costing. We need to consider social consequences and geopolitical risks. Here as an example, the greenhouse gas emission of manufacturing for an electric vehicle versus a gasoline vehicle is shown. So important, this is not about absolute numbers. They're constantly changing and improving, as for example, processes are scaled up for electric vehicles and the manufacturing will be more and more decarbonized. However, it's interesting to see in this graph that battery manufacturing is here actually the most significant and additional carbon footprint which we observe when comparing the electric versus the gasoline vehicles. Next, we can start to look more closely in the battery manufacturing part. Again, I'm not insisting on absolute numbers. They can vary in different reports. Let's just note in the top left figure that the raw materials acquisition plays a very significant role in terms of global warming potential, in addition to the cell production and the pack assembly for a lithium-ion battery. The graph on the bottom left shows that the battery cathode material actually impacts strongly on the total energy demand of the battery production. Here it is more than 1/3 for an NMC111 cathode material. The right graph shows now the material intensities when we change the chemistry of the cathode. More modern cathode materials use less cobalt. So cobalt is substituted more and more by nickel, which ultimately would avoid using a major conflict material, but puts more pressure on the nickel supply. So let's look again at the viability of the substitutional strategy for the battery-powered electric vehicle. We saw before the different greenhouse gas emissions for the electric versus the gasoline vehicle. And under the given assumptions, this was not advantageous for the electric vehicle. Now we go a step further and consider the scenario of a certain electricity generation mix and various total driving distances of the vehicle over its lifetime. We can observe now significant savings in terms of greenhouse gas emissions for the electric vehicle, as we have defined now differently the boundary conditions of our system, and the result is a different one. With a battery capacity of 35 kilowatt hours, that is the sensitivity 2030 light green line in the graph, one can observe that above 30,000 kilometers, a climate advantage for the electric vehicle can be found. At 150,000 kilometers, this climate advantage increases to 40% as compared to the gasoline car, which is a pink line. We expect increased battery capacities over the next years. So if you look at the 60 kilowatt hour situation, the dark green line, and climate advantage can be seen with more than 50,000 kilometers. At 200,000 kilometers, we have again 40% reduction in total greenhouse gas emission for the electric vehicle. Let's summarize. Substitution is one of several mitigation strategies to deal with the criticality of strategic metals. Substitution can be addressed on several levels of technology and material science advancement. The viability of a substitutional strategy needs to be proven by life cycle analysis and life cycle costing. All steps of the value chain leading to, for example, a high-performance magnet or battery, which are the two essential ingredients of electromobility, are subject to constant improvement. Regulations, legislations, or disruptive innovation can change the need for substitution quickly.